you can do that, but then you have to work out the consequences.
It's going to talk about estimating CP-violating nuclear matrix elements from CP-conserving ones, please.
Joe, thank you very much for having me. Let me start by saying I'm sorry I haven't been here before. After agreeing to come, the Department of Energy program manager who gives us the money wanted to visit, and the only chance for her to visit was this Monday. You can't say no to someone like that, so I had to delay my trip. And because especially it sounded like there's some very interesting conversations yesterday I would have loved to hear. I won't have anything profound to say at all, so I'll just have maybe some insights that are predominantly useful for the theorists. And this is a view of the Bay Area, San Francisco Bay Area, and this is the fog of theory. So we think we know what we're doing, but we're peering into the void and we don't really know what's going on, but we like to think we do. Okay. Now, I have one slide of fluff because everybody has to have some fluff, but you guys know why we're here, so I won't even mention it. I just thought this kind of cool picture. There's this excess of 1 part per billion of matter over antimatter, and someone drew a neat little picture. I don't know why matter is red and antimatter is green, but maybe red's the opposite of green. Okay, so assume CP-violating physics is heavy, so we can use effective field theory. And here I mean the standard model effective field theory to encode BSM physics into some short distance operators written in terms of standard model quarks and gluons and other particles. Completely ignore the standard model weak sector mixing because we know it's irrelevant for matter antimatter asymmetry to the best of our knowledge. I'm also going to ignore CP violation in the neutrino mixing matrix, which if you have double beta decay, maybe is a way you can generate excess matter. But first we have to find double beta decay experimentally, and then we can get excited about that. And then if you do that, you have one CP violating operator dimension 4, the QCD theta term, but as we all know, theta is 0 because we haven't found it yet. Or maybe it's irrelevant as we're learning. Okay. So what do we really know in the standard way of discussing things? I'll just stick to that because that's all I'm familiar with at the moment. Is if it exists, theta bar is ridiculously small, and that, as we heard, is the strong CP problem. So therefore, in the absence of some other ideas, we speculate there must be some beyond the standard model physics to give rise to this matter antiatom symmetry. It must be CP violating, and so that will give us some electric dipole moments of standard model particles. And then in the standard model effective field theory, we know there's a lot of operators. So there's dimension 4, a bunch of dimension 6 operators. And here I'm counting these as dimension 6, just assuming whatever it is going to be consistent with electroweak symmetry breaking. So the operator comes proportional to a quark mass. So I'm counting that quark mass as part of the dimension of the operator. In this counting, there's a lot of operators. They all give rise to EDMs. Therefore, nuclear EDMs. What's complicated though is, as we know, like once you introduce one source of one EDM, one CP violating operator, because it's QCD, they're all going to non-perturbatively mix. So even if you only started with one, it will radiatively generate all the others. And so you really have this complex problem where, in order to disentangle what might be going on, it's non-trivial. Very high energies, like way up at the electroweak scale, these operators could be well defined in terms of the standard model effective field theory operators. But down at the QCD level, they're all going to be completely entangled with each other due to this non-perturbative mixing. So from a low energy hadronic perspective, maybe you don't care. You just say, I want to understand, given some operator at a QCD scale of 1 GeV, what kind of EDM will that induce? So that's a question we can ask and try to answer with lattice QCD, and then talk to people who understand how to do the renormalization and run that up to the electroweak scale and talk about some particular model that might generate one of these operators. So I'm going to focus just on a couple because there's too many to think about. So I'm just going to think about 2. So we have the QCD theta term and then these 2 extra operators. This is meant to be a 1 here, not a 3. I think I saw the tau 3, so I wrote 3, but 0 means isoscalar. This 3, which should be 1, means isovector. So I'm ignoring strange quarks. I'm just talking about 2 flavors, again, to make my life even simpler. And then if we have these quark level operators, what we do is we can map them into the chiral Lagrangians. And these will generate in the chiral Lagrangian level here, I got the counting right. I have isoscalar, isovector, and isotensor CP-violating pion nucleon operators. And since trying to calculate EDMs on the lattice is a very challenging problem, as some people here know very well, I thought this, and when I thought about this, I was thinking back in, I think it was 2013, trying to come up with some plan for the Department of Energy to give me money. I thought maybe if we could just calculate these long range couplings, the CP odd pion nucleon coupling, this would already be interesting because in nuclei, at least the bigger nuclei, we have some expectation that long range pion exchange mechanism might dominate the generation of the EDM, in particular for something like radium-225. Not so much for mercury-199, but that assumption that the long pion range effect is the most important is how people take the mercury EDM measurement, the lack of one, and turn that into a constraint on theta. They go through some model where they exchange this long range pion exchange, and they calculate shift moments. I won't talk about shift moments at all, but they calculate nuclear structure corrections and then predict the EDM. And those come from estimating these couplings. Okay. So then, if we take the QCD Lagrangian, including a theta term, we do this axial rotation and put the phase onto the quark mass matrix. Again, I'm learning about everything that's been coming up yesterday. I have nothing intelligent to say about that at all, other than I don't understand it. It's probably intelligent to say I don't know something, or at least it's obvious. I don't know if it's intelligent. So once you do that, you map this into the chiral Lagrangian, and then you can calculate the EDM of the nucleon. So this is what, Kreuter did back in 70 something, 80 something, I don't remember, Kreuter et al. And so here's the graph. So the EDM doesn't come as a leading order operator, it comes as a radiative pion correction. And so here this wiggly line is a photon. The gray circle is one of these modified quark mass operators, which can have a CP coupling. And then I have the standard QCD coupling. And then you predict the neutron EDM. And it's proportional to some coupling G0, this isoscalar coupling, which is dimensionful, by the way. And so G0 is 2 alpha. Alpha is just some, as I've called it, some low energy constant in the chiral Lagrangian. And it's proportional to the operator that gives you isospin breaking times the product of the quark masses over the sum of the quark masses. And they get this log and pi squared enhancement, which is always exciting for trying to compare lattice QCD and effective field theory stuff. Whenever we have nice logarithms, we get excited to look for them. And then some low energy constant, of course, because you have to absorb the scale dependence to make this RG invariant. And then there's this nice relation that the isoscalar coupling, you can relate exactly to the QCD, the strong isospin breaking QCD contribution to the neutron proton mass splitting. And so what's exciting about that, and in particular, this is the mass splitting in the limit that the electromagnetic coupling goes to 0. What's exciting about that from a lattice QCD perspective is now you've related some really interesting physics to something very easy to calculate on the lattice, the spectrum. And so maybe, through calculating neutron proton mass splitting, you can predict the coupling for good old theta term. Can you apply this idea to these beyond the standard model operators? And this is what I started thinking about a while ago. I haven't made a lot of progress, unfortunately. And a few years ago, Jordi, Manuel, and I were curious to see if there are predicted large, strange corrections to this relationship. And what we found through N2LO in 3-flavor heavy baryon chiral perturbation theory is that relationship between the mass and the isoscalar coupling holds to the accuracy we need all the way through N2LO and chiral perturbation theory. Okay, so here I'll make this statement, and I'll even make this statement about SU2. SU3 baryon chiral perturbation theory cannot be used for precision physics. But I think it's fair to say we're not interested in precision physics when we're looking for EDMs, we're looking for order of magnitude. So it's fine. What we want to do is we can still use the theory to qualitatively assess the importance of various possible contributions. And so in this case, the relationship is preserved exactly, except for low energy constants that appear at n to a low. And then we estimate the size of those corrections using naive dimensional analysis. There are 10% effects. And so we say, okay, we have a nice way to constrain the isoscalar coupling from the mass splitting. Okay. Now, before I hop over to the BSM matrix elements, again, this is something other people in this room like Andrea, Cafe know incredibly well. Doing lattice calculations of EDMs is an extremely challenging problem. As in, we don't have a good answer yet. No, maybe Cafe is going to show us an answer, he says. But the point is, these are extremely challenging calculations. So something we do is we say, well, if you believe in chiral effective field theory or chiral symmetry breaking, our understanding of chiral symmetry breaking, probably the best way to get at these is to do the calculation at heavier than physical pion masses and then use the known form to extrapolate down to the physical pion mass. And of course, the point is at the physical pion mass, the noise challenges that come in are amplified in several ways for the EDM calculation. One, the noise of doing a nucleon with physical pion mass is just worse. But if you want to hold the pion mass times the volume fixed as you drop the pion mass, that means you have to increase the size of the volume, and the noise problems for EDM calculations grow exponentially as you increase the volume. So you get hit with a double whammy in noise. And then also the signal drops with the pion mass. So your signal is dropping and you have two sources of noise. Okay. So here though, what I was going to say is I just maybe have some advice. It may be useful, maybe not useful. Yeah, I don't want to pretend it's going to be useful, but maybe it is. So I would say even in SU2 variant chiral perturbation theory, there's some significant challenges I would say that are being uncovered from lattice QCD results. And so it's important to really check the convergence of the expansion to really show that we have the extrapolation under control. And this is not a novel idea. You know, basically this statement is you should take multiple observables related to the same physics and do a global analysis at the same time. Otherwise, you could be missing some relatively important corrections. So here's just an example of what I say challenges for the baryon chiral perturbation theory. So if I just calculate the mass of the nucleon in chiral perturbation theory here to n to a low, we get just generically, there's a constant, the mass in the chiral limit. A term here, I've just written sigma for fun, because it's related to the pi nucleon sigma term. The scale's like m pi squared. You get a predicted minus 3 pi GA squared m pi cubed. And notice, if you believe this is the GA, the same one that shows up as the axial charge, which it is the first order, there's no low energy constant here. So this is in some sense, a prediction of the theory. Of course, these non-analytic quark mass dependent terms are the real predictions in some sense of the effective theory. That what makes them interesting, these infrared enhanced type of things. You get some m pi to the fourth, m pi to the fourth log m pi. Okay, but here's some actual lattice QCD results of the nucleon mass converted in some way to physical units as a function of pion mass and physical units. And you'll see it goes up to about 400 MeV, and it comes down to the physical pion mass. And this is the result of a fit. These are 3 different lattice spacings. I'm using this form of the chiral expansion. And, you know, you can reproduce the numerical data pretty well. And then you do the extrapolation. This purple band here is the continuum extrapolated nucleon mass as a function of pion mass. And also volume corrections are included. So I claim this is, in some sense, a prediction of what the nucleon mass should be as a function of pion mass. And then you'll notice there's this dashed black line here, which is given by 800 plus m pi. So that comes from a fit from 2008 that is completely unmotivated. It's just looking at some old data, like numerical data, please excuse me. And it just fit this line perfectly well. And you can see that the heavy baryon fit is also completely consistent with that within the uncertainties. And so that's, what's that telling you? Well, first of all, okay, minus GA squared M pi cubed. This is also a large prefactor for a term because heavy baryon KPT always gives these extra factors of pi. And that's a negative contribution. The data is going purely up. So if you were to allow GA to be fit in this way, like if you were to try to extract GA by fitting the nucleon mass, you would find GA is consistent with 0. But we don't think GA is 0. We think it's 1.27. So this is what I mean as a challenge in the effective field theory. The effective field theory does not naturally explain a lot of lattice QCD results.
But we know that the impact report has a big delta contribution. Actually, my question is, all the energy constant in this expression are known except for zeros.
Yeah.
If you try to input what we know from Python structure, you get you reproduce the data.
You can reproduce the data. No, you have to have at least one low energy constant beyond M0 that you extract from the lattice results. But yes, you can take known low energy constants from pi nucleon scattering, put them in. As long as you have at least one extra control at this higher order, then you can fit the data. So it's not, this isn't a state.
Consistent with KPT.
It's not inconsistent.
I don't want to be on the records.
What I'm saying is inconsistent is it's not natural, right? In order to produce this, you have to have strong oscillatory cancellations between different orders.
Yeah.
That's unnatural, right?
Oh.
It's not inconsistent. It's not totally impossible, but it's just unnatural. If you put in the delta, the problem is very similar. Yeah.
So it doesn't fix the M by Q.
Oh no, if you put in the delta, actually, if numerically it doubles the strength of the minus M pi cube. So for the nucleon mass, the delta adds coherently with the virtual nucleon delta. These two graphs, I guess now the audience, maybe they can see from the camera, maybe they can't.
They can, we just have to switch on the right decision.
For the nucleon mass, these come with the same sign. They're both negative. So it makes the problem worse.
We have I don't know how much data. We have data of some partial quenched results, which surveillance are lower than the physical ones, where the C is big. And then certainly it deviates from the linear plot that you have.
That's good.
But that partial quench, so we could probably look at them. You know, we looked at before. Looks, you know, you can fit it with the log or M pi cube and so on. But we can look at again with if there's a partial quenched, say heavy baryon and so on, one can probably try to fit them.
If it didn't deviate from this curve at a little bit lighter than physical pi mass, then I get really worried. It has to deviate at some point.
It does, yeah, but it's just, you know.
But so the solution to this is, so one thing I like, so if I want to make a prediction with lattice QCD, the only thing I want to do is I want to fix the light, the strange quark mass, maybe the light quark mass splitting, and the scale. And I don't want to take anything else from experiment. I want to take that, do my simulation, and predict things. And so I think we run into the danger of fooling ourselves if we take some information from experiment, some low energy constants, and then try to fix other ones.
But I mean, Andreas, you know quite well, I don't need the microphone, that most lattice results are inconsistent for the sigma term, which is the leading term after the M0, are inconsistent with what we get from terminology. So why do we use this stuff?
Well, these are spectrum results, which are simple. Getting the sigma term requires taking a derivative. That's much more difficult. And those calculations tend to be done with a 3-point function, which has another host of systematic problems that don't. So my claim is for the 2-point function, the systematic uncertainties that go into extracting the true ground state are under control. And in the 3-point function, as also pointed out by Manuela, it looks like, I think they have a very plausible argument. If you impose a theoretical expectation of the excited state spectrum on the analysis, the sigma term is no longer inconsistent with phenomenology. And so I have long suspected that lattice calculations of the sigma term have underestimated their systematic uncertainty. You know, I can't point to specifically what people have done wrong, but I think Emmanuel and company, they have a very, very strong plausibility argument. I wouldn't say it's a proof because I can tell you why I don't think it's a proof, but I think it's a highly plausible argument.
Yeah, I know, that's one point out. I mean, these things are all related when it comes to three-point function. That's why I agree with the last line. But in GA, I mean, we did the two of calculations, I don't know, 2006 or so long ago. I mean, I was young then, now I'm old. But there you have even stronger cancellations if it were there.
And there, at least with GA, you have large NC arguments that the delta correction cancels against the equivalent of these diagrams for GA between the delta and the nucleon, they cancel. So if you add the delta to the theory, I think you might be able to save the effective theory, but I think without the delta, it's actually problematic. And so the point of this slide though is simultaneously extrapolate. So if you take GA from lattice QCD results and do an analysis of the nuclear mass and GA, that GA analysis will force GA to be about 1.27. And that will force the other low energy constants to respond in kind to agree with the numerical data.
Can you also do a delta? Can you give the overall energy constant? I mean, can you keep a delta correlator and nucleon correlator at the same time?
For the spectrum, yes. For the matrix element calculations, the technology is around the corner. So the lattice calculation would have to involve N to delta transition and delta to delta matrix elements as well as the GA. And I think 2-year time scale, you're going to start to see high quality N to delta to delta type calculations on the lattice. And then you can do this multi-global analysis with the delta.
But one more comment, I mean, one should be a bit careful with the data because in the chiral limit, the data is a heavy state. So I would rather have, I mean, it's much more easy to read the data out. I don't care about phenomenology.
Well, I'll have another slide where I think we have to explore putting the delta in explicitly.
Yeah, but it has to work with also delta because in these things the delta appears in the left in the Lorentz concept. Dynamical delta is not really, I wouldn't believe that.
Well, let me show you something and maybe you can tell me you still don't believe me. That's my prediction. Okay, GA versus the pi mass. I'm not. So here we have this nice percent level determination of GA, and this is a full. This is the same data set that generates these nuclear mass. So this is GA, and we have this nice uncertainty breakdown. You can see it's statistics limited. Clearly, if we just do more precision of the physical pi mass, we can reduce this uncertainty. I guess this is just an advertisement slide. Nothing really interesting here. We're going to have probably a 0.5% precision of GA, but there's this new QED correction. I can move this even. We got the news the other day. We finally got accepted to get published. So we found this QED structure correction. This is again with Emmanuel and some other collaborators of order 2% radiative QED correction to neutron beta decay, which hasn't been picked up in the literature yet. And so in order to actually make use of these lattice QCD results, we have to address the QED corrections. Okay, and here's another advertisement slide. We actually have updates of the physical pi mass. In the old one, you can see the uncertainty in the physical pi mass results is effectively useless for the extrapolation. But with the new supercomputers, they've become useful. And just to give you, this slide is also like 3 years old, but so it's even better now is what I mean. This one green point here cost a whole year on running this Titan supercomputer, which is the old one at Oak Ridge. And then in 2.5 weekends, we got this green one on the new supercomputer. And so the even newer supercomputers are turning on right now. So that's why I'm optimistic lattice QCD will do something more useful soon. Oh yeah, and the other thing is we have additional results at 180 and 260 MeV pi masses. So we actually have 7 pi masses between 400 MeV and the physical pi mass, which I think will really be essential to help understand the convergence of chiral perturbation theory. We can ignore this Bayes model averaging. Oh, right. The reason I want to point this out is because the numerical data for GA, if you do Taylor expansions and you do chiral perturbation theory, the data does not like chiral perturbation theory. So if you fit with chiral perturbation theory versus fitting with just a simple polynomial, the numerical data say distrust chiral perturbation theory. There's nothing deep there. It's not saying it's the wrong theory. The reason the data doesn't like it is because the chiral perturbation theory has strong, again, oscillating contributions. And if you just have a very simple, if you're agnostic about what the fit model should be and ask what's the most natural way to describe some data, if you have a function that has strong oscillating terms, of course it can describe the data. But if you have a simple extrapolation that doesn't need that, the data is going to prefer that. So, okay, that's not.
What's the expansion in KPT? You have an epsilon cube.
Yep. So for GA, you get epsilon pi squared. You get a constant epsilon pi squared, epsilon pi cubed, epsilon pi to the fourth type stuff. And there's log and pi showing up in there as well.
So in your fit, what did you find? Equation, let's say, I guess is the full.
N2LO chi PT goes up to epsilon pi cubed. And then plus counter term means the same fit, but add only the counter term from epsilon pi to the fourth. And so this is a Bayes model averaging. So what this is asking is what's the probability of a given model given the data normalized by the sum of all models you've considered. And this is telling you that the data only gives a 3% weight to chiral perturbation theory. So it really doesn't like it. But this is the chiral perturbation theory fit, and then broken down. A given band is the sum up to that order. It's not just the contribution from that order, but it's the sum up to that order. And this picture sort of tells it all. If you do the full fit, so this is N2LO, which is this formula here, then the NLO contribution has this strong negative correction. So it's just diving away from where the numerical results are. And so then you have to add a large positive term to pull the whole thing back up. And then the 1 plus counter term just means we add this. Okay, this is good. It looks like it's converging, but there's a strong negative correction. And where I get worried is this is all of your 2006 N2 or N3LO 2-loop result. And here, so now I have a 0 degree of freedom fit, so it's not really a fit. But then the problem is once I add this extra stuff, the strong negative contribution becomes even stronger. So when I add the higher order terms, it makes the convergence, the expansion even worse. And you also see this with the nuclear mass if you use Bynen's equivalent formula where you use the renormalization group to some higher order log corrections. It makes the minus m pi cubed even more negative. So whatever's going on, this effective field theory is not a natural way to describe the numerical results. And to put it in more words, oh, right. So here's where I get worried. So GA is ubiquitous in basically all of nuclear physics. Any property of the nucleon you want to know, or any multi-nucleon property you want to know, GA or the equivalent G pi and N is something that shows up everywhere. And so if you have a convergence problem with one quantity, it's like going to impact the convergence of any quantity you want to look at. And this is specifically where I get worried. So this is doing the fit and then asking at the physical biomass in the delta-less theory, what does the convergence pattern look like? And you get a leading order term that's big. Next to leading order is negative. And then N2LO is, in this first line, is opposite sign and bigger. And so this wildly oscillating expansion, I think, to me, that's typically what we teach our students when you have an asymptotic expansion that is breaking down. The observation is you have these wildly oscillating terms that are canceling. And so I say, it's a failed expansion. That's my, so I don't think you'll agree with me, but.
I think this is the whole thing which most people do wrong with all this. What one should really compare is the leading order is 1 plus 2, the next video is 3 plus 4, and the next video is 5 plus 6, because it always comes to even the earth power.
That
I
is
don't think it makes sense to separate the even and the earth power.
that is a clever way you can reorganize your counting to look like it's converging, but the textbook definition is not 0 plus epsilon squared and 1 plus cubed. It's, you know, like what rigorous
Which textbook? There's no good
whenever we study perturbative expansions, is there any rigorous explanation for why you could be justified in taking 0 and 2 and 1 and 3, right?
Of course, that's justified because it is goes back to the Mellon sector. In the Mellon sector, there's a 1 component, 2 is 3, 4 is 1 loop, 6 is 2 loops, and so on. Now in the barrier, it's also an even one, so 3 is 1 and 2, 1 loop is 3 and 4, 2 loop is 5 and 6. So I would, it depends how, of course, you can organize like you can say just by the constant fine for the coefficient, but you can also say go the same 3, 1 loop, 2 loop, and then 3 is 1 plus 2.
For the nucleon mass, NLO and N2LO are 1 loop, right? So that would be how you do the counting.
Yeah, you put them together, right?
Yeah, no, but that would be taking like a 2 and a 3, not a 2 and a 4.
The point is, for example, for this
Yeah.
PA stuff, what we did is this is a fifth order, which is fine. For the horrific calculation was fun, but of course the real this is also including the sixth order where they're counterform. So I mean I would really do these things differently. I would really do 3 together, 1 loop together, 2 loops together. But of course that's a matter of how you define things, and I cannot tell you how to do things, but this is, I think, and if it works with the delta, if it would work with the delta, then things are completely wrong. Because it cannot work with the delta alone because these are only counter terms. There's no dynamics at PA which really would.
No, for
The delta does part of the reorganization.
That's what it does.
It's gonna shield some contribution to.
Then you already do it in a way, but still, for me, 3 is 1 plus 2, 1 is 2 plus 4, and it's better I would like to look at.
you're saying this plus this. These are the 1 loop. Okay, I can look at that too. But yeah, adding the delta contribution,
Rearranges things.
but it comes for GA, it comes with the opposite sign of the nucleon loop. At least gives you explanation why you might not have strong pi mass dependence. Okay. I completely lost track of time. Is there? Okay. Just cut me off whenever. This is again, what is this? I was going to talk about coming back to defining the nucleon mass correction, the isis vector correction to the nucleon mass and how you can get G0 out of that. To make sense of it, you have to define the mass and the QED goes to 0 limit, or come up with a scheme. So, you know, QED corrections and strong isospin corrections mix under renormalization. So there's no unique way to say what's QED and what's strong isospin breaking. But there are schemes which naturally come out of like thinking about the Cottingham, the QED self-energy correction of the nucleon, where you can actually come up with at least the leading order scheme that separates QED and strong isospin breaking corrections. And this is just a discussion of how you might do that. I don't think it's super relevant. I'm just jumping ahead to something maybe slightly more interesting. So here we're actually going to calculate the isovector mass with some lattice results. And the neat thing is we can ignore all the partial quenching stuff. If you look at the proton and neutron mass, I was telling you also that it's these m pi cube terms that are problematic that cause the expansion to have trouble. But if you look at the mass splitting, they exactly cancel. And so these odd powers of the pion mass cancel in the nuclear mass splitting, at least at this order, leaving you with a more convergent expansion. And this is a snapshot of some numerical data. On the upper plot, I'm actually plotting, you can't see by eye probably, but there's actually one's a neutron and one's a proton. And this is just to highlight for those of you who aren't familiar, these data sets are highly correlated. And so you can actually take a correlated splitting and you get something that looks like the bottom plot. So this is plotting the effective mass of the neutron and the proton separately. And this is plotting the effective mass of a correlation function designed to isolate the mass splitting. And you see this incredibly precise ability to extract the mass splitting. This is what the numerical results look like as a function of pion mass. So this is 500 MeV, 420, and 224. And okay, the data looks a little odd, you know, and in fact, there's actually 3 points here at different values of the strong isospin breaking correction. And this is the mass splitting divided by delta. So the fact that all 3 are lying on top of each other is just telling you it's linear in MD minus MU. You're not seeing any higher order corrections at all. Okay, and then here's a cool little fit, taking the formula for the mass splitting. So again, the m pi cubed term drops out. And then you have this, again, delta is MD minus MU over 2. Alpha is the same low energy constant I talked about much before. And then here's this case where you do have also a very large enhanced chiral logarithm. So 6 GA squared plus 1 over 2 is a relatively big number. And then when you fit the data, in fact, it really loves the chiral log. So it's kind of cool. So if you enforce GA to be 1.27, you get a very good fit. Chi-square per degree of freedom 2.73 over 5. I think you know enough to math to see that's going to give you a high quality factor. If you allow GA to float in the fit, it actually picks a value of GA that is at least almost 2.5 sigma inconsistent with 0. So that's telling you this numerical data set does like having that log in there.
But what is really in this formula with GA in the chiral limit? It's not really clear physically. It's not really.
Yeah, well, I don't know if you can choose to reorganize your perturbative expansion in many ways, as you know. You can make this F or F pi, right? And I've written it as F pi. You didn't complain about the F pi. And that's just shuffling some terms at higher order. And so if this is my on-shell pion mass and this is the on-shell F pi, I would argue it's more natural for this to be the on-shell GA, not the GA in the chiral limit.
Yes, but in principle, all these quantities there should be the leading term of the pion mass, the leading term of the pion, the leading term of GA.
Yeah, and all those higher order corrections would go up beyond the order of this expansion, yeah. And so it's
then it's kind of, I mean, come on, this is GA, this is uncertain.
so what's nice is what I'm saying is unlike the nucleon mass, if you look at the nucleon mass splitting, it does like seeing this non-analytic quark mass behavior. And the reason that's interesting is because that's also the same thing that is related to the EDM of the neutron if you have a QCD theta term.
But did you try your model averaging here?
Oh yeah, I have the plot on my computer. Just since you asked, we're doing this live, right? So I can. How do I stop hiding the zoom control?
Oh, you have to go down or up depending where you hide, where you hit them. With the mouse
It says hide. I don't know how to unhide.
But click on zoom, yeah.
Window. Does anybody know how to bring your zoom controls back after you've hidden them? I just want for the others to be able to see the remote.
See the go to zoom.
Yeah, I'm on.
It's a zoom, right? Escape. Show video back.
It's a natural way to stop
Show
the
video
flow.
back.
There's,
No, on to them.
you can see us.
Go to the other show. There's another.
No.
No. Usually in Windows, press escape. Show
There we
from
go.
There you go. Good.
Okay. So you can all come along at the same time. Oh, doing this stupid thing. Okay. Anyway, I think I know how to use a computer reasonably well, and I will tell you I have strong dislikes for Zoom, even though I don't have a better option. But like the forced updates and a lot of things about Zoom are very annoying. Here you go. So what is this? This is a model averaging of doing the fit of the nucleon mass using the chiral perturbation theory fit, and then, there we go, versus a polynomial fit. So polynomial fit has some weight, but the data still prefers the chiral perturbation theory to the polynomial. So that's suggestive that the data, the numerical lattice QCD data, is liking the logarithm. Does that answer your question? Okay. Then we'll go back to here. Back, well, we never left Zoom. You guys can see my mouse, right? I won't bother with that laser pointer. Hide, float. Okay. So what is my point about this? When people are using the expression to extrapolate their heavier than physical biomass lattice QCD calculations of the neutron EDM, and you're putting in this G0, maybe taking G0 from a lattice calculation, maybe, so I'm advocating basically figure out G0 by doing a simultaneous calculation of the neutron proton mass splitting. But the thing to be wary of is because this effectively this coupling you see has a strong biomass dependence, that could mess around with your interpretation of your numerical data as you try to extrapolate the dipole moment down to the physical biomass as well, because you have a relatively strong change in the coupling as a function of the biomass as well. And I'm a big advocate of on-shell renormalized reorganizations of the expansion because they tend to always converge better. And they're also much easier to fit lattice QCD results to the renormalized expressions rather than the bare ones. So this is my little bit of advice for those of you doing lattice QCD calculations and using the extrapolation formula. I would simultaneously fit the mass splitting, but then also be wary of the potentially large pi mass dependence of that coupling. I think it could have an influence on how you interpret the results and the extrapolation. Okay, so Andrea's quiet, so I'm going to hop back to the CP violating operators. So the symmetry that relates the strong nuclear mass splitting to the CP pi nucleon coupling is an SU2 axial rotation, and that's a symmetry of the standard model. And so if we put in these CP operators, we want to preserve that symmetry, and so that means we must have these CP conserving operators as well. And then they transform, so basically you use the same great idea of relate CP interesting CP physics to CP even physics that's much easier to calculate on the lattice. And so you generate these relationship between the coupling and spectroscopic quantities, which are relatively easy to compute. And then from that, again, so here's a relationship between the isoscalar and isovector coupling in terms of, oh, where'd it go? Sorry. The change in the nucleon mass splitting induced by this BSM operator, that's this delta Q Mn. Delta Mn is the nucleon mass splitting induced by strong QCD isospin breaking. Delta Q M pi squared is a shift in, sorry for jumping between capital M and little m, but delta Q M pi squared is a shift in the pion induced by this CP even coupling constant, so on and so forth. And so these are all things that are very easy to calculate with lattice QCD. It turns out there's a little problem with that simplistic formulation that was pointed out by Michael and Chinya. And so based on that, with Chinya, Jordi, Manuel, and I, we have these slightly modified relationships you can use, which are nicer in a number of ways. They remove they get around the subtleties brought up by these two. And also, I didn't write it down, but this difference operator here also subtracts the leading 1 over a squared operator mixing that's induced in the lattice QCD calculation. So there's a nice benefit there. And this R quantity is a ratio of the chromomagnetic condensate to the chiral condensate, so of the vacuum. And then epsilon is just related to the quark mass splitting. So here's some actual lattice QCD results for these. So here is,
Do they need normalization?
yeah, that's why. That's my depressing last slide. So yeah, we can save my depression for the end. Yeah. Here's some results. This is the scalar quark matrix element of the proton. We get a nice clean answer. Here is the chromomagnetic scalar operator in the proton. You can see we can get a nice clean answer. And then here's the isovector operator in the proton, and then the chromomagnetic isovector operator. And just like the QCD isospin breaking operator, we know that this QCD isospin breaking operator, so MD minus MU is roughly equal to MD or MU. And so the nucleon mass, the sigma term and the nucleon mass splitting are both related to quark masses times these matrix elements. So the nucleon mass splitting is MD minus MU times this matrix element, maybe up to a factor of 2. And then this matrix element times the quark mass is the sigma term. And the sigma term is like 60 MeV and the mass splitting is 2.5 MeV. And so we see this order of magnitude suppression between the isovector and the isoscalar operator. And since MD is comparable to MD minus MU, I'm just saying you can look at the size of the bare matrix element and get an estimate of this size difference. And we observe the same thing for the chromomagnetic condensate as well, that the isovector one is suppressed by something like an order of magnitude. I don't know, it's probably, you know, some approximate, I don't know why it's so much smaller. There's probably some neat explanation somebody knows.
What are these two bands here?
So there's two different data sets, which is these two different things. The gray band is a simultaneous fit to both data sets, and the blue band is the ground state matrix element after you've, so this gray band includes excited states in the fit, and the blue band is just the ground state matrix element.
You could just connect this for the extra.
Yes, we haven't done those, but yes, you have to.
No, so they're not in the plot.
They're not in the plot, but we do expect them to be smaller, but they're not enough to give rise to this order of magnitude discrepancy. So yes, we have to compute these as well. We haven't done that yet, but I mean, so here's some numerical results for, this is the proton chromomagnetic condensate. This is chromomagnetic condensate in the proton. And already there's some very non-monotonic behavior going on in these numerical data sets. And so this was, I don't want to, let's just say I looked at this, my grad student worked really hard and I looked at this and I said, oh, something's a little disturbing. And then he graduated and started doing other things. So, and then I haven't been working on it, but the real thing that stopped us was, here's just more examples of, I mean, everything looks like it's roughly lining up, but like this, like in this one, say this isovector matrix shown with the red is the coarsest lattice spacing, it hops up and then really down very strong. It could be because we don't have an exact cancellation. So we haven't done any real renormalization. So it could be that because we haven't done the proper renormalization, the hope that the 1/a² stuff is canceling is not working so perfectly, and the coarse data set will be the least susceptible to that problem. But then also the coarse data set has this very terrible looking behavior. So, but this is the kicker. This is why we stopped. So even though these ideas are cool, the non-perturbative renormalization you need to do is just as terrible as for the EDM. And so there's like 2 physical operators and then there's 17 unphysical operators that appear, because when you do the non-perturbative renormalization, you have to do gauge fixing. So you get these, you have to insert gauge non-invariant operators that mix, and it's just a horrid nightmare. And I was doing this as Andrea was learning about gradient flow, so I didn't get the benefit from these great ideas. But more or less what shut down the project is the grad student graduated and this renormalization problem was very challenging. And I thought, maybe I'm going to do something else with my life. Okay. So I'm telling you some, I think, conflicting things about low energy effective field theory. One, symmetry is amazing. We can use it to construct higher Lagrangians, understand how this BSM physics affects the natural world. And I'm also telling you, baryon chiral perturbation theory doesn't work. At least the convergence pattern is not healthy. Most quantities don't show the anticipated non-analytic quark mass dependence at the physical pi mass or around it. So if we really want, what we should do is run lattice calculations at lighter than physical pi mass to see if these things kind of show up. And because really what you want to do is you want to predict from lighter than physical to the physical point, not the other way around. Because we know at heavier pi masses, things are breaking down. It's not the right way to go, but it's much more expensive to do it that way. So we're not going to do it until lattice QCD is developed to the point that these calculations come for free. No one is going to give you a lot of computer time to do something that's super expensive and it's at the lighter than physical pi mass. But then also look, there's this beautiful chiral log of the nucleon isovector mass splitting. So maybe not all hope is lost. I think my real statement is that if you need both precision and an extrapolation, I claim the SU2 chiral perturbation theory without a delta is not something you can necessarily rely upon. Of course, for a given quantity, it's going to work just fine. But when you look at the global analysis, you're probably going to find tension and low energy constants that you don't know how to quite resolve. And I'm not talking about the experimental stuff. I'm talking about like trying to extrapolate lattice QCD results. Because really what we'd love to do is extrapolate lattice QCD results, determine low energy constants, and find that they're consistent with all the stuff that's been extracted from all the phenomenology like Ulf has been doing for a while. And for the EDM stuff, I think it's a case where we don't need precision, but we do need to extrapolate. And so maybe I think the real message I want to say is I think a good strategy would be to generate multiple observables that are related and do a simultaneous extrapolation. You'll probably learn something more from this than just trying to extrapolate a single observable. And I have temporarily given up on the CP conserving matrix element to get CP odd matrix elements, unfortunately for myself. But I'm sure other people will do it better than me. Okay.
Thanks, Andre, for a very, very interesting talk. Questions in the audience or at home? Oh.
Yes, thanks for this very nice talk. Can you repeat again when you say you want to extrapolate to get the EDM? So exactly where do you like to extrapolate from, and what would prevent you from working directly at the physical point, and so you won't have any need to extrapolate?
So Left Cafe surprises us today. The calculations of the EDM, so we have all these signal to noise problems and lattice calculations.
Yeah.
And the EDM has, and then you want to do a calculation of the nucleon at the physical pi mass, that's already a noisy problem. But then again, if you want to hold m pi L at 4 compared to a 300 MeV, you have to make the volume twice as big.
Okay, okay.
And
No,
then
I
the
understand
EDM
the
has-
problem. Just where do you like to extrapolate from at? Yes, I missed, probably you said, but
So I'm not doing it, but I think
Yeah.
Cafe and Andrea are working like 400 MeV.
Okay. okay, yeah, that was the question.
And so 400, I don't have this. Okay, this isn't a good way to show it. Here we go.
I want to see a signal, so if I increase the mass, the signal.
Okay, so I don't have it on this plot,
Uh-huh.
but this, oh no, I have it right here. The key. Okay,
Sorry.
this is 200 MeV.
Oh, good, good,
This is 426 MeV.
very good.
And so that, remember that. And then if I go here from 426 to 200, you're coupling.
That vertical line is the physical line. Sorry, now I get it now. Sorry.
And the coupling at
Okay.
in this range here is what? It's like 30% enhanced over the coupling at the
Okay,
physical
no,
pi
I
mass.
see.
And so that could impact the extrapolation.
I see. Thanks. That was
I guess you suppose you can do some reweighting to get using an example, do a bit of reweighting to get the physical point, right?
Yes, but this would be really interesting, right? Because if you have a quantity that has some very strong non-analytic quark mass dependence, that's the perfect place to test your reweighting techniques, because if that's where you think they would fail, because you have some, it's not like a perturbative shift in the observable, but there's a really strong log driving Yeah, and this curvature is driven by the competition between the log and the counter term.
Mhm.
So that would be actually kind of interesting to test.
Yeah, but I thought a couple of years ago, people thought, reweighting in quark masses seems to be reasonable,
I think,
working. Yeah.
right. So, for example, the nucleon axial radius, the proton charge radius is an example where you have a log and pi enhancement, right?
Mhm, mhm,
And in fact, you
right.
go in divergence as you go to the chiral limit until you
Right,
include radiative pions.
Right.
So quantities like that or like this, where you have a strong log affecting,
Mhm.
I think the reweighting is all based on the assumption that if you do a tiny perturbation in the quark mass, your observer will also have a tiny perturbation, right?
Mhm.
And in this case, you don't have
log.
that. But
Yeah,
if
that's a
you
concern.
showed that the reweighting worked in such a case, that would be a very strong indicator that your reweighting is under control.
Yeah.
I'm experimentalists who also do some stuff on measuring the electromagnetic polarizabilities of nucleons and maybe a spin polarizability. Can you say something on the prospects of kind of precisions to extracting these from lattice QCD?
That's another calculation I started and I gave up on.
Okay. Because, well, what are the challenges?
Yeah, so I did it with the background field. What are the challenges? The challenges are, if you want to do the electromagnetic and polarizabilities, you just need a constant electric or magnetic field. And for the size of boxes we're using, if you want to quantize the magnetic field or the electromagnetic fields correctly, they're very large magnetic fields. And I think they're sufficiently large that you might begin to worry that the nice, the math will get a quadratic correction from the magnetic polarizability, electric polarizability. That could be breaking down at the size of magnetic fields you have access to. If you want to do the spin polarizabilities, then you have to have a gradient in your background field. And we don't know how to properly quantize a background field that has a gradient. Now, Café is doing the hadronic tensor, where he's putting two currents in at the same time. And so it seems plausible in a few years that you might start seeing 4-point functions where you actually put in two currents and then you could directly access all these polarizabilities. What's the time scale you want them on?
Our neutron magnetic and electric polarizability, we get results on 3 or 4 years.
So I think 3 to 4 years for neutron electric polarizabilities is very doable for lattice. Because those are the easier ones to do. I know, like Andre Alexandru, yeah, he's working on this. But again, so he tried to include the, so normally when we do the calculations, we do what we call electroquenched, where the C quarks don't have any charge, it's only the valence quarks. And he tried to put in the electromagnetic corrections from the C quarks through reweighting, and it was incredibly challenging. Like he needed something like 500,000 statistics where the calculation itself needed 10,000. So there's still some puzzles to be worked out, but I think 3 to 4 years is a realistic time scale to have good results.
Skylar, you want to go ahead with your question?
Yeah, thanks. So you said a couple of things very early on that I kind of wanted to follow up on, even though it might diverge from the main message. And this was about the domination of the long range CP violating pi-NN interaction. So as far as I'm aware, I guess when these calculations were first done for undeformed nuclei, this was probably Dmitriev and Senkov and John Engel. There was an argument that the nucleon EDMs, the valence nucleons, were a subleading contribution in comparison. But does this also hold up in the deformed nuclei, like radium or radon, where there's an enhancement factor that we know enhances the pi uncoupling, but what then happens to the valence nucleons?
So I'm going to first say you should ask John Engel.
Yeah, probably. Okay.
And then second, I'm going to repeat some words that I've heard from John Engel and Wick Caxton. So I can't justify these words, but I'll at least tell you what they tell me. And that's for radium-225, which is octupole deformed. There's something about the octupole deformation that makes the nucleus stiffer, and therefore the nuclear model calculation of the shift moments more reliable. compared to mercury 199. And then the enhancement in the radium-225 is coming from the very near degeneracy of the parity even and odd state. I think it's like 55 keV, if I recall correctly.
Yeah, sure. So you have a couple of things providing these enhancements, and the small energy splitting, the parity doublet is one, but you also have the beta 2 and beta 3 moments. And then this is all multiplying the matrix element for CP violating new physics. But what I wasn't clear on is if this only applies to the long range physics, or if the valence nucleon EDMs are similarly enhanced, even though they may still be subleading.
Again, so John can give you details, but my understanding from John is that the estimate that the pine exchange mechanism, this long range, is still holds for radium-225, and the ability to calculate the nuclear shift moments, which mask the EDM, are more reliable for radium-225 than they are for mercury. And I think that's one of the reasons that theorists are more excited about radium-225 as well for the EDM measurement.
Sure. Okay. And then, sorry, maybe the closer connection to the main thrust of your talk is people like Jordi de Vries have mentioned a few times that it's kind of a shame no one can be really motivated to do theoretical or experimental work really intensively on, say, few body hadronic parity violation, where you have a chance to measure some of these, to trace the symmetry violation, let's say, within the standard model. You may not have much of a chance to see beyond standard model physics there, but it would give us the tools, at least conceptually, to also do that work for CP violating new physics. And then on the experimental side, but also for theory, is there any chance to have access to that stuff through atomic and molecular systems rather than the nucleons?
I'm not the person who can give you a good answer.
Fair enough.
What I can say is with parity violation, so 2 nucleon parity violation is an example where once we get things under control and 2 nucleon lattice QCD calculations, you could actually do something with lattice QCD to calculate the 2 nucleon, the isotensor 2 nucleon parity violation pretty nicely. Once you go to isovector, isoscalar, you run into a lot of problems with renormalization and disconnected diagrams. But so work that Barry Wick and Susan Gardner did, actually, they highlighted the isotensor 2 nucleon parity violation as a particularly interesting quantity to understand, because in the large NC power counting that emerged in the last couple of years, that's one of the 2 big operators.
Mm-hmm.
So maybe, yeah, I won't say 3 to 4 years, but beyond the 4-year horizon, lattice QCD may actually help with parity violation in the 2 nucleon hadronic parity violation.
Okay, and that doesn't all fall under the umbrella of these things that were just too challenging with your 17 extra operators. And
so when you talk about isotensor, so delta I equals 2,
yep,
then there's no lower dimensional operator that can mix with. So it's
okay,
much easier. Yeah.
Great. Thanks.
So anytime you maximize isospin or something like that, so you can't close a quark line back on itself. Like if you imagine just drawing the valence quark lines and some initial to final state, any diagram, any physical process you can think of where you can't draw a quark line back on itself is much easier to calculate with lattice QCD than one where you have to include a quark line that can come back to itself.
Sure.
In case you want to dream up of something to do. Something to propose some poor lattice QCD person to do.
Sounds good. Thanks.
Thank you.
Other further questions? Okay, if not, let's thank Andrea again.